Hi, today we are going to find the boundary conditions at conductor free space interface. Before starting doing this mathematically, let's try do this analytically. Firstly, I draw an arbitrary conductor. We know that conductors, to reach to the state of the equilibrium, the charges are going to depart the middle, and they will distribute themselves on the surface of the conductor. And due to this, inside the conductor we have no charge density. Okay, inside conductor the charge density is equal to 0, rho equals 0. And according to Gauss's law, which is according to this formula, which is Gauss's law, we have no electric field inside the conductor. And regarding to the surface of conductor, these charges will try to maintain the state of the equilibrium. So due to this, we have no tangential electric field. What I mean, we have no electric field which is tangent to this interface, because if we have an electric field tangential to the surface, this electric field will affect the other charges and they will move them. So the state of the equilibrium will be violated. And due to this, we have no tangential components for electric field at the interface of conductor. Okay. E sub t denotes the tangential components of the electric field. Instead of this, we will have a normal component of electric field. The reason of this, that the surface of the conductor is equipotential. Okay, and due to this, an equipotential surfaces will be constituted around this conductor, something like this. This magenta colored surface is the equipotential surface, and we know that the electric field for all time is normal to these equipotential surfaces. So we have electric field which is normal to the surface of the conductor, okay, which is equipotential surface in the first place. And accordingly, we can conclude that at the interface of conductor free space, we don't have a tangential electric field, but we have a normal electric field components. Normal electric field components exist. Okay, now let's do this mathematically. I will start by finding the tangential components of the electrical field. I have this interface, which is between a conductor, which is the top media, and a free space. This small figure is the side view of the interface between conductor and free space. I'm going to draw firstly a rectangular contour between conductor and free space, okay? I will call this contour by ABCD, and it's going to have a width of delta W, and it has a height of delta H. Okay, I'm going to take the integral around this closed contour for the electric field, okay? As this circle denotes that this contour, or the path that we are integrating around, is closed. Okay, what does this line integral yield? Just recall the curl of the electric field. We know that the curl of the electric field is equal to 0. By applying Stokes' theorem, we will find that the path integral of the electric field around the closed surface is equal to 0. So this equals 0. Okay, just take the integration. Let's call the electric field inside conductor by E1, okay, and the electric field inside the free space by E2. Okay, and this electric field will have a tangential component, okay, which is denoted by E sub t, okay, and normal one, let's say it's upward, which is En1. And the same thing for the free space. We have two components, ET2 and ET2 and ET1, which denotes to the tangential component and the normal component respectively. Let's say that the direction of this path is counterclockwise. Okay, now let's start integration. I will make delta H for this path approach 0, as we want to find the tangential components. Okay, we want to find the tangential, the electric field at exactly the boundary between the conductor and the free space at the interface. The dot product between the electric field E1 and this piece of the path AD will yield the tangential component of this field. Okay, because the normal component is going to vanish because it's perpendicular to this surface, to this path, and the dot product between two perpendicular vectors is equal to 0 times delta W. Okay, and regarding to DC and BA, both of them are going to vanish, so I'm not going to include them in this integral. Plus, and I forgot to say that this path delta W is opposite in direction to the tangential component, so I will add the negative sign. And regarding to this, the normal component is going to vanish. We will end up with the tangential component, which is directing like this rightward. Okay, and as the tangential component and this path CB both direct to the same direction, so both of them will have a positive sign, and the length of this is delta W. The answer is 0. We can rewrite this by we can simplify this into. Okay, and as we see from this equation, we can conclude that the tangential component, or the tangential components of the electric field at conductor free space interface is continuous. What I mean by continuous, there is no discontinuity when we move between these two interfaces, as E sub T1, which is the tangential component of the electric field inside conductor, is equal to 0. So the tangential component of the electric field at free space at the interface is also equal to 0. Let me summarize this by ET1 is equal to ET2 is equal to 0. Now let's find the normal components of the electric field at the interface. And for this, I'm not going to take the side view like this. I'm going to take a top view. This arbitrary surface is the interface between the conductor and the free space. Let's say that above this interface we have a conductor, and below it we have a free space. And we know that we have only charge density on the surface of conductor. So this surface will have a charge density equals to rho inside the conductor, which is above this surface. We have no charge density. Above it we have no charge density. Rho is equal to 0 because it's conductor. I'm going to draw a pillbox. This pillbox stands on this surface and it extends below it. Okay, I'm going to draw it. The shaded box is this piece of box which is below this surface, and the other one is above it. Let's say that the area of the top surface of this box is equal to A. Now I am going to find the electric flux through this box. We know that the electric flux is the surface integral. I'm going to find the electric flux at the electric flux or the electrical flow through the top face of this box. So I'm going to take the integral around A. Okay, What is the right hand side of this equality? Just remember Gauss's law, which is determining the divergence of the electric field. By applying the divergence theorem, we are going to take the volume integral for both sides. The volume integral for the divergence will end up with the surface integral, okay? And this, the volume integral for the charge density is the charge enclosed, Q enclosed. Now let's take the integration by making the height of this box approach 0. Let's say that the height is represented by delta H. Delta H approach 0. Okay. And now we have two surfaces and two components of electrical field. We have electrical field above this interface. Let's say electrical field 1, which is the electrical field inside the conductor, and E2 is the electrical field inside the free space. Let's say that both of them, for simplicity, let's say that both of them are upward, okay? Let's make that product between E1 and the top face of this surface. We will end up with E1 times the area of this surface, which is 1. And regarding to the sign, the area vector for this surface is also upward. It's the same direction for E1 vector, plus for the other electrical field, E2, we're going to make a dot product between E2 and the bottom face of this pillbox, which is its area vector directing downward, and the dot product will end up with E2 minus E2 times A. The components will be normal components, okay? Because tangential component will vanish in this case, because tangential components are perpendicular to the area vectors. Let's continue this inequality. We said that this equals the charge enclosed divided by E divided by epsilon. I mean, the charge enclosed in this pillbox is equal to the charge density, which is the charge density of the conductor, times the area of this pillbox divided by epsilon. And due to this, A is going to be cancelled out from both sides, and we will end up with E1 normal minus E2 normal is equal to rho divided by epsilon. And as we are in free space, we will add epsilon sub 0. And from this we conclude that the normal components of the electrical field at the interface between conductor and free space is not continuous. We have discontinuity at the normal components of the electrical field in the conductor is equal to 0, but they exist in the free space. Okay, and according to this conclusion, I will made E1 sub n is equal to 0, which is the normal component inside conductors. We said that inside conductor we have no electrical field. So the electrical field outside the conductor, or the normal component of the electrical field outside the conductor in the free space, which is caused in the free space because of the conductor, is equal to the charge density of the surface of the conductor divided by the permittivity. At the end, I'm going to summarize by saying that the tangential components at the boundaries of conductor in free space is continuous, and the normal components is discontinuous unless rho equals 0. If rho equals 0, both the tangential components and the normal components are continuous. And I want to mention at the end that in some textbooks, instead of using E sub t for the tangential components, they are using E with these parallel lines, okay? And for the normal components, instead of using E sub n, they are using E with this sign, which is representing the orthogonality of this component of the electric field to the surface of the conductor. This is the end of our lecture for today. See you.